Hello everyone, I am Dr. Suja Alex. I thank Dr. Meena Kadigari, ISET TVM, for this opportunity. This session highlights the unique challenges in federated learning and gossip learning, contributions, and the proposed novel gossip learning framework of the research work titled Decentralized Gossip Assisted Deep Learning Model Training for Resource-Constraint Edge Devices. This paper was recently published in IEEE Transactions on Computational Social Systems. In the field of federated learning, some of the challenges are single point failure, straggler effect, and data heterogeneity. In traditional federated learning, the central server is responsible for coordinating the training process, aggregating the model updates from the coordinating devices, and sending back to the coordinating devices. Here, if the central server fails or becomes unavailable, the entire system could be compromised. In traditional synchronous federated learning aggregation, the global server keeps waiting for all the coordinating devices to compute their computations before it proceeds with global aggregation. This slows down the overall system due to the limited computational capacity of some edge devices. This is known as a straggler problem. In federated learning, the presence of non-identically independently distributed data complicates the model aggregation process. This leads to the performance degradation. To address these challenges, gossip-based learning has been emerged as a promising solution. In gossip learning, the decentralized communication among the edge devices fosters knowledge discovery. This approach facilitates collaborative learning that allows the nodes to access and utilize the diverse datasets without depending on the central server for the coordination. Gossip learning algorithms iteratively update the model parameters based on local data and exchange the information with the neighboring edge devices in a randomized manner. Traditional gossip learning approaches face some challenges because it follows a ring topology that uses random gossiping to select a specific device as an aggregator. This approach limits the connectivity only to the neighboring edge devices, hence, it fails to foster full collaborative learning. The main contributions of the proposed approach are lightweight model extraction and designing a novel gossip learning framework. They developed a novel gossip assisted deep learning model for the resource constrained local edge devices problem by enabling decentralized and serverless training. This solves the risk of single point failure and improves knowledge discovery with a higher prediction accuracy. This figure shows the proposed gossip framework that consists of a set of distributed N devices like sensors, which is denoted as ED, resource constrained edge devices represented as E, and a resource rich centralized cloud server connected within this network. In the proposed framework, initially the centralized cloud server trains a deep learning model over a publicly available large scale dataset using a heavyweight deep learning model to extract a lightweight model and further deployed on the edge devices. The main objective of this work is to minimize the loss on each edge device and achieving a loss reduction rate across all the edge devices through weight aggregation. In the proposed gossip learning strategy, heavyweight deep learning model is developed initially and converted into a lightweight deep learning model for the edge devices. Here, D dash is a subset of the original large-scale dataset in the cloud. The proposed methodology involves training multiple neural network models that include artificial neural network and convolutional neural network architectures. There are R models generated at various edge devices, and only K models are selected for further analysis. The selected models are optimized to become lightweight using various model optimization techniques focusing on quantization and pruning. The sizes of different lightweight models are compared using the threshold model size ST to find the lightweight models. The best lightweight model is extracted by evaluating based on a predefined threshold model accuracy theta. Initially, all edge devices interact with the cloud based on their connection setup. When the first edge device successfully establishes a connection with the cloud, it becomes the source edge device of the network. The next stage involves setting up of gossip-based environment for gossip communication and enabling a collaborative learning of the model. If the initial source edge device is not selected, the configuration of the edge devices are adjusted and the connection requests from the edge devices are sent to the cloud to establish a source edge device. Later, if a new edge device wants to join the network or if the source edge device fails, the standard Bully algorithm is executed to select a new source edge device for the network. The source edge device interacts with the cloud to get updated best lightweight model and it passes the aggregated weights to other edge devices. The source edge device aggregates the weights of model parameters of the participating edge devices and transmits them to requesting edge devices. The source edge device also uses the aggregated weights to retrain itself and adding the edge devices to the gossip network. Hence, the devices are connected to the source edge device have a duplicate of the source edge device model. During the initial model training, each device trains on its local dataset, which is not visible to other edge devices in the network. The weight updation of the models is performed using this equation. Here, Wi denotes the weight of ith edge device, R denotes the updated step, eta denotes the gradient step size, and del is the gradient of last L in the previous iteration weight Wa of R minus 1. So now the gossip learning framework is established. The algorithm 3 represents the operations involved in gossip communication. Initially, the weights of trained edge devices are propagated to the source edge device. Then the source edge device performs weight aggregation. Once the aggregation is done, the aggregated weights are distributed to all other edge devices in the network. The previous model accuracy is denoted as sigma pt, which is compared with the current model accuracy sigma ct on different iterations to update the model's previous weights that is passed to other devices during the next iteration of the gossip learning for weight aggregation. The algorithm 4 suggests the flow of gossip learning across diverse edge devices within the gossip network. The algorithm starts with the checking for the source edge devices. If the source edge devices are active, then the initial training for all the edge devices are started and the model parameters are generated with accuracy. Now these model parameters are sent to the source edge device and the aggregation is performed. During next iterations, all the edge devices receive the aggregated model parameters, retraining of the model started and the current accuracy is same. The difference in the previous accuracy and the current accuracy is stored in the variable th, which is then compared with the change in accuracy delta to identify the entire convergence of the network. Here, delta is set by experimenting over various iterations. In successive iterations, all the identified slow edge devices send their updated model parameters to the source edge device along with their neighbors. This can reduce the communication overhead. To address the non-IID problem, each edge device is retrained on the limited instance of data. In further iterations, the existence of source edge device is checked by the network connections, and if it fails, then the bully algorithm immediately activates and selects the another source edge device for the network. The analysis utilized two datasets, MNIST and CIFAR10. These datasets are split into subsets of different sizes and distributed them across various edge devices. Here, figure 4 and 5 represents the non-IID distribution performance. The test split across different devices is kept unequal, providing a maximum test split across different devices. During the training, specifically, the first edge device exhibits low accuracy compared to other edge devices. Through successive iterations, all the edge devices improve their accuracy and contribute to enhancing the performance of the others. In figure 8, the performance of proposed gossip learning against standard techniques such as federated learning and centralized learning across different datasets are characterized by IID and non-IID data. The figure 9 compares the total request sent by the edge devices to the source edge device for aggregation. While comparing these requests with standard federated learning and centralized learning, gossip learning sent a fewer requests because it introduced a single edge device as a source aggregator. This unique architecture significantly reduces the communication overhead by minimizing the aggregation request sent to the aggregator. As a result, latency also reduced. Thank you.